तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been discussing the drain saturation current using the Shockley's model. Okay. And there the assumption is that the drain current saturates when pinch off occurs at the drain edge. So, that is actually the voltage across this, the total potential drop there is V p 0. So, when V p 0 is the voltage drop across that, when you have V d sat here, V d sat plus V b I minus V g s is equal to V p 0, that is the condition. Now, what we have discussed later on is that the just a couple of things. So, this assumes actually low field mobility, that is okay if the fields are high, and I d saturates due to the channel pinch off at the drain end. I am just putting it in words whatever I said now, and that is the equation that we used for saturation voltage. V b I minus V g s plus V d s is the potential drop across the depletion layer, that is when it is V p 0, the current saturates. Okay. Now, we discussed yesterday that such a situation is questionable, because as you move from the source end to the drain end, the current density keeps on increasing. Because the current density increases, velocity increases. In fact, electric field increases, because after all what we have used is the equation J is equal to Q n into V. Now, area falls, so V increases and the electric field increases, and when you reach this end, you will have actually velocity saturation. What you are telling is the real saturation in current comes up. We discussed this last time. The real saturation is due to velocity saturation at this end. Now, whether pinch off takes place at that point or not, that issue we will see. Okay. It could be so that when the velocity saturation takes place, it is almost closing off at the drain end, that is the pinch off. So, let us see that. Okay. So, what we did is the electric field effect can play a very dominant role in saturating the current. Strictly speaking, the velocity field characteristic is actually something like this. The electric field versus velocity, electric field versus velocity. In silicon, if you take, you know that it is not going up like that, but it goes up like that. After about 20-30 kV per centimeter or volts, okay, kV per centimeter, then it saturates. That can be met very easily. When the channel lengths which are 1 micron, if the channel length is 1 micron, if the voltage drop is 2 volts, okay, V is equal to 2 volts, and if L is equal to 1 micron, V by L is equal to 20 kV per centimeter. So, that can be met very easily when you go to channel lengths which are of the order of 1 micron, and if you go down below that, you are sure to have very high fields. Okay. But now, what we are trying to find out is how to incorporate this saturation effect. It becomes very complicated if you take the entire distribution. If you take gallium arsenide, it may go like that. It will saturate maybe even at a smaller value, and it may come like this. It may be matching close to that. it becomes really complicated in those situations. To get an idea, to bring out the effect of velocity saturation, okay, that is the first order thing to do analytically. You can bring in all these effects by numerical methods later on. So, what you do is take, instead of taking all these things, take velocity field characteristics as shown in the graph there. Okay. We will go back to this graph here. Okay. Instead of plotting it all those variations, do piecewise linearization. That is what is done here. Okay. So, avoid all those peaking and everything, take it as linear up to certain electric field. Velocity proportional to the electric field for E less than E of s, and till E equal to E of s, E is the saturation field, and V is equal to saturation velocity for electric field greater than saturation electric field. Okay. So, at this point the velocity is mu n into E of s. So, saturation velocity is obtained right from there. So, this you make this assumption. Now, you find out what is the current, saturation current, what is the saturation voltage, would it correspond to channel pinch off, and when channel pinch off occurs, definitely there must be velocity saturation. Other question you are asking is, when the velocity saturation takes place, will there be channel pinch off at all? Okay. So, those are the things which we are going to examine, but now in the case of Shockley's analysis, you had the advantage of assuming what is the saturation voltage is. Okay. That is V D sat plus V B I minus V G S is V P 0. V P 0 is known for a known thickness and doping. Q and D A squared by twice epsilon or epsilon 0 is V P 0, that is a known quantity. For a given V G S and V B I, immediately from that equation, you know that V D sat. Once you know V D sat, you substitute in the equation for the current, where the V D S is there. That is how you got the thing. So, one of the unknowns, there are two unknowns, I D sat and V D sat, both are there. If you know one of them, you can find out the other one, or there must be two equations which you can solve to get I D and V D sat both. So, here you do not know at point the V D sat is taking place, but you know that it would saturate when the velocity saturates at some point. That concept is made use of. Two unknowns, I D S and V D sat. So, what we do now is divide the channel into two regions. Okay. Now, let us go back to that. So, here let us examine the two cases. This case I have drawn the depletion layer, Shockley's model, I D S is a pinch off. Drain current saturates when the pinch off takes place. So, what we want to examine is whether we get the same condition for the situation where the velocity saturation takes place. In fact, there is no doubt that current saturates because of velocity saturation. Okay. Otherwise, if it is closing completely, as some of you are raising some time back, current will fall down to 0. So, it is we said qualitatively it is a dynamic equilibrium, and the dynamic equilibrium has come due to velocity saturation here. It could happen so that this width is close to A. Okay. Now, the other condition is I D S due to V equal to V S at the drain end. Now, please understand once again, both the cases the current saturates due to velocity saturation. I pointed out to you yesterday, even without a junction, when you go to high fields, current can saturate in the resistor. Okay, we examined that in the last lecture. So, here what we tell is, I have plotted two things. One, a channel which is long, other one channel which is shorter. So, the fields in this region will be higher compared to the fields in this region. It could so happen that velocity saturation can take place here even without pinching off. So, what you are telling is VDS the drop across the channel divided by length is the field, that could be close to the peak electric, the saturation field. So, the difference between these two is no difference, both of them current saturates due to velocity saturation, but in this case the current is saturated before pinch off, because before pinch off itself there is enough voltage drop, there is enough field, whereas in this case it has allowed the pinch off, that is the difference. Okay. Now, we will take that equation which we derived. So, what we are trying to do now here is this. We will take the equation which we used from this end to this end, same as what we have used with the V is equal to mu into E, because we are now taking the case like this. That is what we are doing. That means, till the electric field is equal to saturation field, I can write V is equal to mu into E, and from the point at which V is equal to the E is equal to saturation field, beyond that point velocity saturation is there. Okay. Beyond that point the channel cannot shrink. So, this is the condition which is equivalent to the pinch off. That is, what we are telling is, from here to here as we move, field is small here, as we go on field becomes larger and larger. At a particular point at which velocity saturates, at a particular point at which the velocity saturates, okay, E is equal to E of S, and from that point onwards you cannot write V is equal to mu n T, and from that point, at this point you write current is equal to, current density is equal to Q n into velocity saturation, and in this point you write current is equal to, current density is equal to Q n into mu n into E, and that is the equation that we have derived. So, in the channel region, not at the drain end, other portions, we can still write this equation which we have derived in the previous two lectures, that is G naught into V d sat. We are talking of the saturation current. In fact, what we are doing is, let me go back to that, what we are doing is, we are taking a situation where this velocity saturation is present here, velocity saturation is present here, and in this portion there is no velocity saturation. So, up to this portion I write that equation, and under that condition current has saturated, because velocity saturation has taken place at the drain end. Is it okay? So, now this is a very familiar equation for you. Okay. It is written by writing J is equal to Q n into V into area. I am rewriting that equation. See, all that we are trying to do is writing the two equations, because after all we need to find the I d sat and V d sat, we need two equations. So, we write one equation in the region. Okay. Let me put that instead of showing it with hand. That is the source, that is the drain, that is the gate. Okay. So, this is a VGS. So, what we are trying to say is, you have a depletion layer like that. It may not have, it may or may not have pinched off. What we are saying is, for this condition that I have drawn here, velocity has saturated here, and beyond this point V is equal to mu n into E. That is what you are trying to point out. So, in this portion I write the same equations which we have used for Shockley's model, where V is equal to mu n into E. So, I get one equation for I d, and when the velocity is saturated here, the current is saturated. So, in that equation I say whatever V d is there is V d sat, and whatever I d is there I d sat, but I do not know both of them. So, to know both of them, I write one more equation at this point. At this point, I do not use this equation. What we use is this portion. So, at this point, current density is equal to q n into velocity saturation. Okay. We will see how it works out. And current is equal to q n into velocity saturation into this area. And once you find out this area, that is equal to, that is this height is equal to a minus h, and h is related to V t sat. So, we get an equation, one equation from this portion, writing V is equal to mu n into E for in the current equation, and another equation between I d and V d, writing the current expression for current here using that portion. That is all what you are doing. You are trying to get two equations. Okay. So, the first equation is like this. Now, instead of keeping on writing this long equation again and again, okay, what we do is normalize IDS, saturation current. Please note, I do not know what is IDS is, I just said IDS is the value you get when V d is equal to V t sat. That is all what I have done. So, IDS is equal to G naught. I pull out this, I have multiplied by V p 0. So, I take inside also divide by V p 0, multiply divide. So, you get V t sat by V p 0 and 2/3 of V p 0 to the power 3 by 2, because this is pulled inside. See, I have multiplied here by V p 0, I have to divide everywhere by V p 0. So, you get 2 by 3 V p 0 to the power of 3 by 2, that is taken inside. So, what is happening now is the terms inside the bracket, each one of them is divided by V p 0. So, you normalize this with respect to V p 0, because V p 0 is the quantity which is decided by the particular device, doping and thickness of the A layer. Okay. So, you have got that term there, I call it as UDS. Instead of writing V d sat by V p 0, I will call it as UDS, normalized value of drain source voltage. And I d, I can normalize. What is this quantity? See, all these are normalized with respect to V. These are ratios only. So, this has dimensions of G naught into V p 0 has dimensions of current, voltage into conductance. So, I d s divided by G, this quantity, that is the normalized value of the current, normalized value of drain source voltage, normalized value of voltage at the source end, you call it as UGS, the whole thing, and this you call it as UGS plus UDS. Okay. I have rewritten that equation now. IDS is IDS by, we will go back to that equation again and see whether we have written it correctly. IDS by G0 V p 0, that is normalized value of IDS, is equal to UDS, which is nothing but V t sat divided by V p 0, the first term, minus 2/3 of UDS plus UGS to the power 3 by 2. Just go back once and see, minus 2/3 of UGS is this quantity and this is UDS, VDS by V p 0. So, that is how you get that, plus V b I minus V g s divided by V p 0 to the power 3 by 2, which is that. All that we have done is, the whole thing comes in one line now. Okay. The whole thing which was looking so terrifying here with all these big half a page occupying here is now single line, but the identity is maintained, normalized with respect to that. You can write simpler equations in a simple form by normalizing. So, this is the one equation that we have written for current in this portion. I have both the IDS and UDS, both are unknowns. I write another equation here. How do you write the current? Because here the velocity is not given by this, that is given by velocity saturation. So, what we do now is write the current at the drain end. It is due to the velocity saturation at the drain end. Okay. And what is the current actually? J or ID is equal to Q n carrier concentration into velocity saturation into area. This I am writing it as, what is n? Electron concentration, which actually equal to the doping concentration. So, that is N d. Velocity saturation of course, which is mu n into E f s. We can write it afterwards if you like. Area, this height into W, and that height is actually equal to, this is h at the drain end and this is A. So, this is actually h minus A into W. Okay? Huh? That thing people are alert or not. Okay? So, that is equal to Q N d into W into V of s into W into A minus s. That is the area. That is what we have written there. Okay. Where this equation is put down here, where h is actually the depletion area width at the drain end. Shockless analysis said h is equal to very close to A. It cannot be A. Then you can see the current becomes equal to 0. Now, let us further simplify it. So, I can write, all that we do here is Q and D is retained, velocity I can write it as mu n into E of s, because we are looking into the saturation velocity, which is mu n into V of s if you look into this particular graph. V of s is mu n into E of s. Okay. We are substituting in that particular velocity saturation mu n into V of s. Okay. Let us go back to this slide now and see. So, we have got velocity is that. Oh, this V s is not there actually. Maybe I think I should cut it off right away here. I will take a minute for me, but I think we will take it off right away here, because we have substituted already for that. Okay. So, is it all right now? So, you have got now that mu n d mu n into U of s W into A into 1 minus h by A. Okay. This is the problem of cut and paste, you cut and paste and add that mu n into U of s. Anyway, now we have removed that. Q n d into mu n into W into A, I retain all those terms. Now, the rest is just manipulation. You have written the two expressions for current, one is this, other one is this. Here you wrote velocity saturation. Let us go back to that. So, what we have done is, we have done this now, substituted V of s equal to mu n into U of s. Okay. And then what I do is go ahead further. I just remove that U of s there, pull all these together, Q n d mu n into W into A, just I remove that, put it here, multiply by L, divide by L. And this is obvious to you why I am doing. What is this particular term? This is the channel conductance G naught. This is actually sigma, this is the area of the channel divided by length, sigma area by L, that is the conductance, and this is LEFS. Okay. Into 1 minus, now we write for a expression for h by A. What is A? just to recall once again, okay, I will put it down here. V voltage, whatever voltage is there is related to, I am sorry, V p 0 is the standard formula. So, A is proportional to root of V p 0 and H here is proportional to whatever voltage is present across that, square root of that. So, ratio of H and A, H divided by A is square root of whatever voltage is present across that divided by V p 0. What is the voltage present across that? V b I minus V g s plus whatever voltage is present across that, and we are saying that is the voltage at which current is saturating. So, that is why at the drain end you got H is equal to V b I minus V g s plus V g s, which is sat divided by V p 0. So, that is simple. Now, you write the normalized equations. Okay. So, what I did is this is J naught multiplied by G naught, multiply G naught by V p 0, divide by V p 0. Okay. So, G naught V p 0 into L E S by V p 0 and terms within the bracket 1 minus, I will write that so that it is clear to you here. See, I d s is G naught into L E s into 1 minus square root of V b I minus V g s plus V d sat. Oh, I am not overstepping into that, divided by V p 0. So, what we do is this quantity is G naught into V p 0 into L E of s divided by V p 0 multiplied by that quantity, and what is inside is actually equal to 1 minus V b I minus V g s divided by V p 0 is U g s and V d sat divided by V p 0 is U d s. So, that is what we have written there. Okay. Now, I think we should have reason to be happy now. Why? Not because the lecture is over, because we have got two equations A and B. A is this one, which relates I d sat with U d sat, U d s, and B is another equation which relates I d s with U d s. Two unknowns, you can evaluate them. Okay? This is a statement which you should understand. We have computed the current here by using the linear relationship. You have computed the current here using velocity saturation. A is written for this portion current, B is equation B is written for this portion. Now, the current computed using that and this are the same thing. So, equate both of them, you can find out V d sat. So, that is the equation B, right hand side of equation B, and this is right hand side of equation A, that portion. The currents are same thing in the same device. Okay. Now, what is alpha here? It is again writing one term for this particular quantity. Alpha is L E of s by V p 0. Okay. This quantity is referred to as alpha just for writing purpose. There is no, it is not like the current gain or things like that. It is actually channel length to the saturation voltage, how much it is compared to the pinch off voltage. So, that place this term alpha, which is the ratio of this channel length into the critical electric field or saturation field divided by V p 0 plays a very important role in deciding whether whatever we have writing down earlier Shockley's model is correct or not. Comes straight from here. Alpha therefore is equal to this quantity, entire big term. Now, if UDS plus UGS equal to 1, UDS plus UGS equal to 1, what happens to alpha? Infinite. Okay. So, UDS plus UGS equal to 1 gives alpha, actually alpha equal to infinity, I am putting alpha tending to infinity, or if you want to be soft on that, alpha is very much greater than 1. That is the meaning of that. Or you can put it other way, if alpha is very much greater than 1, UDS plus UGS equal to 1. This indicates LES divided by EP 0 is very much greater than 1. That is the meaning of that. What is this condition? This condition that we have written here turns out to be true when that is satisfied, or it is closer and closer to be true when this is larger and larger. What is this quantity? Write down, put it in the, remove the normalized thing, you will recognize it. UDS is VD sat divided by VPI, VP 0. That is UDS. Second term is, what is that? VBI minus VGS. This is the potential drop at the channel, this is the potential drop across the depletion layer at the source end, divided by, that is what you have written. What is this condition? This condition is, take this VP 0 to the other side, VBI minus VGS plus VD sat is equal to VP 0. Okay, this is what you should recognize. So, this condition turns out to be, yeah, VBI VD sat I am right at an angle, VDS sat plus VBI minus VGS equals VP 0. Okay? That is the condition. So, what we are telling is, when alpha is very much large compared to 1, that is when LES by VP 0 is very much greater than 1, the saturation, velocity saturation takes place. That condition we have used, but when the velocity saturation takes place, this condition is satisfied. That means, in long channel devices, channel length is long, whatever Shockley has been telling or writing, the condition for saturation holds good. Pinch off takes place, or at least it is close to pinch off. If real pinch off takes place, that will be infinity, but now this is larger than 1, maybe 3, 4 like that. So, what we are telling again is, if the channel length is long, okay, by the time you reach that field there, let us say E s is a field, average field, L into E field. So, if that is long, okay, that becomes very large by the time the high field is there. Okay. So, that voltage becomes large, so that it reaches pinch off. Either way it is true. Supposing pinch off voltage is small, even if the channel length is small, if this is very small, you can satisfy that condition. Okay. So, what we are trying, let us go back to that graph and see it once, just for the, maybe I do not do that. Okay. So, what we are trying to say is the drop here is sufficient enough so that it close this if L is long. That is the meaning of that. If the channel length is small, that will not happen. Okay. But if the channel length is small, with a small voltage, you will have high field is achieved. It may not close at all. Okay. That is the other condition. So, obviously, when the L s is smaller compared to V p 0, you will not have this condition satisfied. We will see what happens there. In fact, we will have a situation where the general equation can be derived, and people have played games, in the sense game is not real game, played with the equations and extrapolated, interpolated, etc., got some analytical expressions which look same as that mu C oxide W by 2L into V g s minus V t n whole square with the factor. We will see that. Okay, we have just, so this is actually Shockley's model we have discussed just now, that is condition 1, alpha very much greater than 1. Okay. The other condition, see, if this becomes equal to 1, that is Shockley's condition. If this term, when the voltage reaches saturation, it is less than V p 0, the channel is not closing down. So, if this is less than V p 0, V d sat alone will be even less than V p 0. See, V d sat plus some quantity is less than V p 0. What we are telling is V d sat plus V b I is less than V p 0, that is channel not closing down. That situation, this plus that is less than V p 0, means this voltage is definitely less than V p 0. 3 terms are there, out of the 2 is knock out, that is much smaller. So, that is this quantity is less than that. Now, what we are writing is V d sat, approximately we can put it as L into E of s. This of course assumes the electric field is there everywhere, okay. But actually if you move from this end to that end, electric field is E of s closer to this point. Okay. So, V d sat actually is less than L into E of s, because E is less than E of s here. V d sat is the voltage drop across that. It is L into the average electric field there. The average electric field is less than E of s, because E of s is highest here. Okay. So, L into E of s by V p 0 is less than 1. Is that clear enough? See, we have arrived at, I will go through it quickly once, if you do not, if I have gone too fast on that. These 3 terms equal to V p 0 is Shockley's condition. That is valid when alpha is greater than 1, L E s by V p 0 is greater than 1. We are trying to see what is the situation when L into E of s is less than 1. In fact, we are going about it other way, because we understand this term clearly. So, out of these quantities, I remove this quantity. Okay. So, if all the 3 terms together is less than V p 0, therefore, this term alone should definitely be much less than V p 0. Now, I am removing this, taking it to the other side, V d sat by V p 0 is very much less than 1. What is that condition we are trying to see? Okay. If V d sat is very much less than V p 0, okay, I will put that on the board. So, we are taking a situation where V D sat is by V P 0 is very much less than 1. What is V D sat? It is a voltage drop across this portion, and voltage drop across that portion I can say is channel length into the average electric field. And what is the average electric field here? That is less than saturation field, because peak electric field is maximum here, it is less than that. So, average electric field is less than EFS. So, if this is less than that, which means actually L into electric field average by V P 0 is less than 1. Average electric field is less than that. So, this is less than 1, average electric field is less than EFS. So, L into EFS is definitely, if I replace this by this, okay, that will be given much less than that. Okay. Anyway, on average what you can say is V D sat by V P 0 is less than 1. So, L into EFS, even if you take the maximum thing, L into EFS is less than 1. Okay. At the best case you can have that. So, you can have this quantity less than 1. In other words, alpha less than 1 or LEF less than 1 corresponds to that situation. We are indirectly going backwards now. See, I could have written straight away this and gone into that. What I have done is, I have taken that equation where the pinch off does not take place. When I write this condition, pinch off does not take place at velocity saturation. That condition corresponds to that. Okay. You can take that V D sat is equal to that maximum field itself, LEFS, that is less than 1. Okay. Go back to that. Velocity saturation throughout. Now, worst situation. We say this is much less than 1. Okay. Now, let us go to that. ID sat is actually equal to, what is ID saturation? This I hope you agree, because this equation that we have derived by writing the current here. Okay. Now, what we are telling is UDS is very much less than 1. That is the one, because we are replacing V D sat by almost equal to L into EFS. So, this is less than 1. Okay. Now, when you say UGS plus UD sat, UDS, this term is that quantity, and this quantity is very much less than 1. I am knocking it out, because it is very much small compared to 1. So, what we are telling now is, I can write an equation for the IDS, but involved some of these things, but not very complicated. All that you realize is which is small quantity. So, I am neglecting this. If I write like this, what is the meaning of this? The meaning of that is, you have got velocity saturation throughout the channel. Okay, let us put that down here now. Things get little bit bleak, because we are looking into an extreme situation. The electrons, when they enter itself, have reached with velocity saturation. Okay. They already acquired the velocity saturation. They are not just getting into this portion, they are getting from the inner portion. If that is the situation, once they reach this point, if there is velocity saturation, what will happen to the depletion layer width afterwards? This is velocity saturation. When you go beyond that point, velocity cannot increase, because saturation velocity. J is equal to Qn into Vfs. Current is equal to Qn into Vfs into area. Vfs does not change, N does not change, A cannot change. This will remain the same thing. If it remains same thing, what is the meaning of that? What is the drop here? Very small, that is the meaning. If there is no drop, there cannot be any current flow. Okay? It is very small. That means you get very high fields with very small drop. That is possible when you can get very high fields here, because field in this portion must be greater than the saturation of field. You can get very high fields, very small voltage drops if length is very small, short channel devices. So, we are driving ourselves into a device which has got short channel length so small, such that even with small voltage drops across that, you will have velocity saturation, then that will be the thing. Now, you can see UGS, that quantity is VBI minus VGS, compared to that, that drop is small. So, this is a situation you have got velocity saturation right through the channel. That is possible if you are launching the electrons right into the channel with the velocity saturation, or they just gain immediately the velocity saturation. Okay. So, few things now. I think this I am just now we can just zip through, because the concepts are over. LES, that is alpha LES by Vp 0, if it is very large, that is long channel devices or pinch off voltage is small, such devices velocity saturation takes place when pinch off takes place. They coincide. The velocity saturation and pinch off coincide. That is why shockless theory survived so long, because we are talking of channel lengths which are long or which are pinch off voltages are small. But the moment you go to shorter channel devices, you will have velocity saturation, but pinch off will not take place. Here pinch off has not taken place at all, where there is velocity saturation right through, there is absolutely no pinch off. Okay. So, pinch off need not take place for current saturation. Okay, that is the situation, and you can write this entire thing. I am just rewriting that. You can derive it with a different approach. Okay. I write the whole thing again, that you can skip all these, because you get the same equation whatever approach you write. So, Vd sat is actually Le of s, okay, which is less than Vp 0. In fact, there is no need of going through this, I just rewrote it in a different approach, but we have got the whole thing condition satisfied for that. Now, let us see the general case. The most general case is obtain, you have to solve these equations. You have got velocity is equal to mu n into E, this portion. At the drain end, this is the portion. I have put those two things together. Okay. You have to equate these two, find out UDS from these equations, numerical solution you have to do. If I have to find out UDS, once I know UDS, I can actually find out IDS by substituting in either this or this. Okay. In other words, we have got two equations, we have equated two to get one equation. Alpha is this. Okay. We have made use of this. Next, what we can do now is, okay, we are interested in finding out, let me quickly go through that. We are interested in finding out the value of UDS by using equating these two. So, there are some clever people who did some solutions. What you do is equate these two, get alpha. This is what we have used already. Now, alpha depends upon L into E of s by Vp 0. Alpha is okay. What we are trying to see is, as a function of alpha, what will be the UDS for a given VGS. Alpha is decided once you decide the device, because E of s is fixed. that is the property of the device material, that is fixed. Okay. You have taken that by linearizing the thing, maybe 20 kb per centimeter or 10 kb per centimeter, depending upon whether you talk of silicon or gallium arsenide. Okay. So, that is fixed. This is fixed once you fix the device. What about this quantity? That is also fixed. So, for a given device, if I am changing alpha for a given doping and thickness, I can change L and C. So, one of the ways that people have done is do that alpha versus UDS. Using this equation, you substitute. The best way to do is for a given gate to source voltage VGS, UGS. After all, you cannot vary all the things. You find out alpha versus UDS. How to do that? Change UDS and find out what is alpha is. Straight. If you find alpha, decide alpha and find UDS, it becomes more complicated, because both numerator and denominator you have got. For a given UGS, put for different values of UDS what is alpha is, you get that. Okay, you can do it numerically, or you can do this substitution and find out, and then that is virtually cooking up, in the sense fitting the parameter. So, what people did, in fact, the actual person who did this, Michael Schur from Rensselaer Polytechnic, he published quite some time back this result, because to simplify, to get analytical solutions, numerically, if I do not have to go for numerical, analytically you can do by substituting UDS, different values, find what is alpha for a given gate to source voltage. So, I found that you can fit into this expression. Okay. You can fit in this expression, because after all each curve is plotted for one UGS. You can get number of curves like that. I have plotted one curve for one UGS and put the analytical expression corresponding to that, close fit. And once you get an expression for UDS in terms of UGS, okay, you go back and substitute in equation 2. What is equation 2? Okay, let us go back. This is equation 2. IDS is equal to, see what you have got now is, for a given alpha, we know what is UDS is from that expression, and in terms of UGS. So, you get IDS versus UGS. So, I substitute for UDS in that equation. Okay. I think I should put that down here. Okay. So, you get IDS equals alpha into 1 minus root of UDS plus UGS. I got an expression for UDS from here, which is alpha into 1 minus UGS divided by 1 plus alpha plus minus UGS. So, I removed this quantity in terms of UGS. That means, I get IDS versus UGS. That means, once I know what the gate voltage is, what is the gate voltage UGS, what is UGS? VBI minus VGS divided by VP0, and IDS is actually drain current, IDS divided by G naught VP0. So, what I am trying to point out is, you know UDS in terms of UGS by extrapolation, interpolation, etc. You know IDS in terms of UGS. You get the transfer characteristics. Okay. That is what you got. Substitute there, again an approximation is done, you get this. Hereafter it is very simple. You do not have to worry about the path. The path is that of extrapolation, interpolation to get a fit into that formulas, complicated formula. Simplified, you get this expression. Now, once you do that, I multiplied by, this is normalized value, IDS divided by G naught V P 0. So, that is that. I remove the normalizing quantities and write it in terms of that. Go back to the original equation. Okay. you get this, and then I get G naught by V p 0 into okay. All that I have done is I pull this V p 0 out. So, you get V p 0 gets cancelled with that 1 by V p 0 square, I get this. Just simple. I have not made any modification there. Same equation, rewriting this, you get that. I multiply this by 4 divided by 4, I get again okay. What is this quantity? Minus V threshold voltage. So, this whole thing is V g s minus V threshold whole square, and this term is 4 alpha by 1 plus 4 alpha and G naught by 4 if I put, that is that. Okay. What is this first term? I multiply again by that. This quantity is a familiar term for you. I will go through this again next time, because what you are showing is ultimately you get the same expression that you get using the Shockley's equation, except that you got this particular term. We will start right from here next time, go into this. Okay. Then we will see, compare with some experimental results. In fact, it is fair that these things are discussed right in this discussion when they bring in the experimental results. So, I will talk on that in next discussion. Okay.